Hey everyone, in this video I'll introduce a variety of topics related to heat. These include temperature, heat transfers, and energy units. So really in this video you're getting an introduction to a topic of study called thermochemistry. And thermochemistry is the study of the heat energy that's given off or absorbed during a chemical reaction. Now we can probably think of lots of chemical reactions that give off heat, like this bonfire. That wood burning is a chemical reaction, and of course it gives off heat. So if you were to study that heat, how much of it and what it does once it's released by the fire, you'd be studying in the field of thermochemistry. So let's start off by clarifying what we mean by heat energy. Heat energy is the result of the movement of atoms and molecules within a substance. So imagine something that feels hot, like this cup of hot chocolate. It feels hot because the particles within the hot chocolate are moving more quickly on average, or they have more kinetic energy. Compare that to some ice cubes, which are definitely colder. They're colder because they have slower moving particles with less kinetic energy. A lot of the times people get heat confused with the idea of temperature and think they are the same thing, and they're definitely not. Temperature is simply how we measure the heat within an object. So if the object has a higher temperature, you're simply measuring that it has more heat, or that the particles are moving faster in that substance. Conversely, a lower temperature object has less heat, which means its particles aren't moving as fast. Those are some of our really important key ideas for this video. Make sure you pause and take a minute to write them down. Now, most of the time when we're experiencing this idea of hot or cold, what you're really experiencing is a heat transfer, because heat can transfer from one object to another whenever those two objects are in contact with one another. And a good rule of thumb to use here for envisioning that heat transfer is that the heat will always flow from the warmer object to the cooler object. And this is something we know from our life experience. Imagine picking up a cold bottle of soda. In this example, your hand is the warmer object, and it's in contact with the soda, which is the colder object. So according to the principle, your hand is transferring heat to the soda because your hand is warmer and the soda is colder. That's why the soda feels cold. What's actually happening is that you are losing the heat from your hand, so your hand gets the sensation of cold. Here's another example. Imagine putting a cool spoon in a hot cup of coffee. Here the coffee is the warmer object, the spoon is the colder object, so heat flows from the coffee into and up through the spoon. In both of these scenarios, the warmer object will cool down. So here my coffee over time started warm, but of course it's going to get colder as it transfers its heat to the glass and the spoon and other things in the surroundings. At the same time, the colder object will warm up. The spoon started colder, but it's now getting heat transferred to it from the coffee, so the spoon will get warmer. And this heat transfer happens until both objects are the same temperature. Once they're the same temperature, there's no more direction for the heat to flow. This is called thermal equilibrium. These are some more of our key ideas. Make sure you pause, take a moment, and write them down. So let's take a minute and talk about what's happening with the particles within these substances as the heat transfer takes place. So when the two objects come in contact with each other, the faster moving particles start bumping into or colliding with the slower moving particles. Here in our coffee example, the coffee particles were warmer, meaning they're moving more quickly. The spoon particles are colder, meaning they're moving more slowly. And these faster moving coffee particles start bumping into and colliding with the particles in the spoon. As they do that, they cause the particles in the spoon to start moving faster too. And since we've made the particles in the spoon move faster, we've increased the temperature of the spoon and we've given it more heat energy. Here's a nice visual model for this process. At the beginning, you can see the water particles here are represented in red because they have more heat energy and are moving faster. The spoon particles are represented in blue because they have less heat energy and are moving more slowly. The line represents the point where the water particles come in contact with the spoon. This is where the faster moving water particles collide with the particles in the spoon and make them move faster too. As the spoon particles start to move more quickly, you can see that they change to red as heat energy is transferred into the spoon and the temperature of the spoon increases. And the last thing we need are some units for measuring heat energy. Just like there's many different units you can use to measure temperature, like Fahrenheit, Celsius, or Kelvin, there's lots of different units for heat energy too. The most common one is the food calorie with a capital C, and yes, the capital C matters. This is what we see on the back of food labels in the nutrition facts. In science, we use the lowercase c calorie, which is different than the capital C food calorie, or the joule symbolized with a capital J. Here's some conversions you can use to convert amongst these different energy units so you can answer questions like, how many joules of energy would your body have access to by eating 1 serving of Cheetos? You can see on the nutrition facts label that 1 serving of Cheetos has 160 food calories. That's 160 capital C calories, so I have to convert from this into joules. The first conversion I noticed that might be helpful is that there's 1,000 lowercase c calories in 1 food calorie. So using dimensional analysis and canceling off capital C calories top to bottom, I can find out how many lowercase c calories there are by saying that 1 capital C food calorie has 1,000 lowercase c calories. Now that I've got lowercase c calories, I can answer the question by converting into joules with a second conversion factor. Of course, I'm going to put lowercase c calories on the bottom so it cancels top to bottom, and finally change that into joules. The conversion tells me that every 1 calorie has 4.184 joules, and my conversion steps are complete because I'm left with the units joules on top. The only thing left to do now is the math. 160 times 1,000 times 4.18. This works out to 669,440 joules. Make sure you take a minute to pause and write down the conversions between these energy units. And that's it for this video. Here's a brief summary.